So I'm going to talk about Heegaard Floer homology. So for most of the talk, Y will be a closed oriented three-manifold. And I'm going to talk about a construction that associates to such a three-manifold some graded abelian groups. They have different versions. The simplest one is denoted by hat. And there is more structure on it. There will be some actions, and also the Floer homology groups will be decomposed according to spin C structures. But this is so today I'm going to give you the short introduction of what these things are good for, and later we'll discuss the construction. This is a joint work with Peter Oswald. And in fact, the plan is that he's going to talk about the more advanced stuff in his lecture series. Okay, so the first thing is that there will be more than one construction. This is the simplest. They are related constructions. That have slightly different notation. There is the plus version, there will be a minus version, and there will be also somewhat simple version, which we call infinity. And all these homology groups will be related to each other. There will be some maps between them, and sometimes those maps are also carrying extra information. Another feature of this whole thing is that, right now it's related to three manifolds, but as it turns out, it's also related to cobordisms. So if you have two three manifolds, Y1 and Y2, and a smooth four manifold, so W is smooth and also oriented, then it turns out that the four manifold will induce a map between the Floer homology, this Heegaard Floer homology groups of the two sides, so there will be a corresponding map between the two. And the same is true for the other theories. In fact, there is a version of this which is for closed four manifolds, so there is another version, closed, smooth, oriented for manifold. And this invariant is sort of natural analog of Zerberg-Witten invariant, so there will be a map from the space of spin C structures that Ron was talking about in his course to C. Somehow here the main idea is that, of course, this is a closed four-manifold with no boundary, but you can cut out some balls from the two sides. And then this is a cobordism, but unfortunately the invariant is not really this invariant. The cobordism induced by this map, turns out that's not really interesting, and neither the map induced on H plus or H minus, but instead some kind of mixed invariant that basically uses on this side the Floer homology groups HF minus, and on this side the Floer homology group HF plus, and in the middle you have to do some extra things. So this is sort of a more complicated version, but eventually you can get an invariant which is, I guess, a closed analog of Zerberg-Witten. In fact, could be the same invariant, but the construction is slightly different. In a completely different direction, turns out that the Floer homology groups that we discussed for closed oriented three manifolds have a refinement, and this refinement is for knots in three manifolds. So here K is a knot. Then we get a refined invariant. So some kind of invariant that corresponds to the knot, and and it will be interesting even in the case when Y is S3, so that's a special case. That I guess Peter, or perhaps even I, will talk a little bit more. So right now, you see that these invariants have something to say in three dimensions. There is a four-dimensional version of it. There will also be, I guess, a one-dimensional version for knots. As it turns out, the two-dimensional things are also interesting. Surfaces will play an important role in this theory, and in particular embedded surfaces. In three manifolds and in four manifolds. If the main idea is that if you fix a homology class in a three manifold or in a four manifold, then you can represent those homology classes by embedded surfaces, and represented by embedded surfaces. And it's easy to see that if you have one embedded surface representing a homology class, then you can always just enlarge that surface by adding an arc to this surface, maybe a really small arc, and then add an additional handle along that arc. So if I have a genus G surface representing that homology class, then I can easily get a genus G plus 1 surface representing the same. So it doesn't make sense to ask for the maximal genus of surfaces representing a given homology class, but on the other hand, for the minimal genus, that's an interesting problem. So as for the minimal genus of sigma representing a given homology class. And turns out that this minimal genus problem has a relationship both with the Floer homology and also to these four manifold invariants. Basically, if you know some embedded surface is representing certain homology class and you know the genus of them, that gives you some restriction on how complicated these Floer homology invariants could be, which backwards you can sometimes also use and say that for certain 4 manifolds and certain 3 manifolds you cannot represent homology classes with a certain genus. So this is already something about applications. Sometimes you can, let me be more precise. You can say non-trivial things about embedded surfaces. And this is easiest to discuss in case of knots. So let me start with that. So some applications. So this is supposed to be just an overview, and hopefully we'll discuss this in more detail later. So first, some definitions. Okay, so K is a knot in S3. Now this is the trefoil. Then a ciphered surface is an embedded surface with boundary so this would be this whole space is S3, and this is an embedded surface with boundary with the property that the boundary is so ciphered surface for the knot K is such an embedded surface that the boundary of the surface maps into the knot. Okay? So if you want to see an example, let's see that in case of the trefoil, you could take the inside disk, and you can also take the outside disk embedded. So let's try to do that. Inside there is a disk, outside there is another disk. Maybe it's slightly misleading. Usually we draw the knot in R2, but think of it as in S2. So there is the infinity is also part of our picture. So then we have this disk and we have the outside disk, and for these crossings we introduce a twist like that. Is that okay? So topologically what we get is two disks that we have some bands connecting them, right? So eventually this is going to be a surface. It's not very hard to see, in fact. Could that be a homework? That if K is a knot in S3, then there are ciphered surfaces. So the tempting way to prove this is to and just do the same as before, right? But you have to be slightly careful. For example, here I took these two regions, the inside region and the outside region, right? But I could have done something differently in this picture. I could have chosen this region, and that region, right? And in fact, if I band these things together, it's true that I will get a surface, but it will non-orientable surface, right? Because when I go from here to here, I switch the orientation, and there is this I do this 3 times, so I get back the opposite orientation. So there is still something to do to prove this, but it's not terribly difficult. So if you haven't seen it before, then I hope that either that Cameron will tell you the proof, or you can do it. Okay, so this is a ciphered surface, and an invariant that you can define out of that is called the genus of the knot. And by definition, this is the minimal genus of sigma, where sigma is a ciphered surface. For most knots, especially for the easy knots, the genus of the knot is not terribly hard to compute, although there isn't an algorithm to do that for a generic knot, which is reasonable. But still, this is a relatively easy invariant to compute in explicit examples. There's another invariant that's somewhat harder, so it's another definition, which is called the vol genus. And we are doing almost the same things. We have the knot K in S3, and we are also looking for embedded surfaces bounding that knot, but now we give us more room to do that. We don't necessarily want an embedded surface in S3, because it's going to call the vol genus, we want to do it in the 4 ball. So here I take the 4-dimensional ball whose boundary is S3, and now I'm looking at embedded surfaces, but embedded surfaces that could lie in the 4 ball. Okay. So we are taking surfaces that are smoothly embedded in B4 with the property that when you go out, then the boundary of sigma will map to the knot, and it will be a sort of product light at the end. And the vol genus is, I guess, the minimum of genus of sigma, where sigma has this property. And it's easy to see that this vol genus is less than equal to the genus. This is true because if you have a surface that's in S3, then you can just push it inside B4, and then we'll give you a surface that satisfies this condition. It also makes sense to look at some examples. So genus of K equal to 0 means that the knot in S3 bounds an embedded disk, right? So if it does that, then we can use this embedded disk to isotope the knot into a very small circle, right? So clearly this implies that K is the unknot. On the other hand, there are lots of knots for which the four-ball genus is 0. So another example, I guess, that also something that you can easily do if you want to, is to take any knot K, make a connected sum with K with the opposite orientation. So this is the mirror image of K. And this corresponds to connected sum. So you have here the knot K, here you have the knot K with the opposite orientation, and you just add them up. And I guess the homework is that the four-ball genus of these is always 0. And the proof is that you can explicitly find an embedded disk in the four-ball that bounds this thing. Right. So these are some invariants for knots, and there are some interesting problems, especially for the four-ball genus. Turns out that this four-ball genus is, well, in some cases you can bound it, and you can find sharp bonds. Even for some relatively easy knots, this could be hard to compute. And one special case is when, so example, when K is a torus knot. So what is a torus knot? So we can look at the torus two different ways. First of all, in S3, you can take the standard torus, just basically take a knot, take the unknot, take a small neighborhood of that. So take this torus right here. And the torus knot, by definition, is a knot that you can isotope to lie completely on the boundary of this thing, so completely on this torus. So the unknot is a torus knot, but you can also do something different. You can maybe go around this way a few times and also in this direction a few times. So and maybe that's hard to see, but if you really think about that, it's the same knot that we have started before. So if you think of the trefoil, then you can imagine that this could be put on the boundary of a torus, right? And similarly, you can write down much more interesting knots. Let me do a slightly more interesting. So here you have 4 strands. I do this once more. And I do it. and then you close it up. And more generally, what you could do is to think of the torus as R2 modulo the translation actions, and then you take, I guess, here this is P and this is Q. These are two numbers that are relatively prime. And you take the straight arc connecting 0, 0 to PQ, and note that if you write that in the torus, then it will be a closed circle. It will be a closed circle because this point is the same as that point, and because P and Q are relatively prime, it will not self-intersect itself, and it will not wrap around the same circle several times. So anytime PQ is relatively prime, you can just write down this knot, I mean this circle on the standard torus, and write it in this picture. Say maybe this circle corresponds to this circle right here, and this other R corresponds to that circle. Then what you get will be a knot that will go P times in one direction and Q times in the other direction. So this would be, I guess, the 3-2 torus knot, and this would be something like the 4-3 torus knot. And it's okay. It used to be a conjecture, but it's a theorem of Kronheimer and Novka. That says that the four-ball genus of the PQ torus knot is equal to P minus 1 times Q minus 1 divided by 2. Here the point is that it's easy to prove that there is a surface bounding this PQ torus knot that has this genus. The hard part is to show that there isn't another surface that has smaller genus. The first proof of that was using Donaldson invariant. And there is also a proof. You can use Zeiberg-Witten invariants with the techniques that Ron is talking about. Also turns out that this four-ball genus is related to this Heegaard Floer homology for knots. And with some work you can also prove the same, and turns out that this Heegaard, right, that in some cases this is actually computable. These cases include the PQ torus knot, so there is also an alternative proof based on this. So this is the easy lecture because I can just talk about the applications, don't have to actually prove anything. So in the same fashion, let me mention some other directions that this could be used for. So it turns out that these Floer homology invariants, while not very easy to compute them in general, satisfy a nice thing, namely that when you have a 3-manifold and you modify it locally, making surgeries on it, then the invariant changes in a controlled way. So let me talk a little bit about surgeries. I'm sure Cameron will talk more about that. So here we have a knot K in a 3-manifold Y, and if you take the tubular neighborhood of K, that is always diffeomorphic to S1 cross D2. So what you could do is to take out the neighborhood of the knot, which is this S1 cross D2, and glue it back, but glue it back somewhat differently. You really would like to change your 3-manifold. So what we are doing here is we take Y minus the neighborhood of K and glue back this S1 cross D2 using some diffeomorphism on the boundary. Now here F is a diffeomorphism between the boundary of Y minus the neighborhood of K to the boundary of S1 cross D2, which is clearly just S1 cross S1. So here you are using self-diffeomorphisms of the torus. Turns out that in this picture the only important part is so the resulting manifold is determined knowing the homology class so the homology class of let's see, a point across the boundary of D2, which is a circle inside the homology of the boundary of Y minus the neighborhood of K. So what is the circle in this torus that will bound the disk inside the other side? And in case the knot is null homologous, for example, in the case when Y is equal to S3, there is an easy way to see what are all the possible surgery you can do. So here there is your knot, and there are two generators of the first homology of the boundary, namely one is the meridian and the other one is the longitude. This would be a circle in the boundary of K that has linking number 1 with the original knot. So using these two generators, instead of saying that you fix a homology class, here you can talk about numbers. So in this case, the surgery can be specified by just saying that the boundary of this point cross boundary of D2. Maybe I should say F star of D, F star inverse. Sorry. Will be some p times the meridian plus q times the longitude, right? This is z plus z. So here you have some p and q which are relatively prime. And so knowing these two numbers will specify for you the surgery. Now, in general, there are some relationships between the Heegaard Floer homology of three manifolds when you fix the knot and doing different surgeries on them. And the special case of that, so I guess I want to say that HF hat of YF, Y, I guess P over Q, so I'm sorry. So let Y P over Q K denote the resulting manifold. For that, if Y is R3, I already described how to find these numbers P and Q, because you have these special generators, the meridian and the longitude. In general, the meridian is always well defined, modulo plus or minus 1, but you have to fix the longitude, which I have to fix one circle that goes around. After you do that, you can still write down the same numbers P and Q, and then this makes sense. And then if you have that, then you can write YPQK is the resulting manifold that you do after you cut out the knot and glue it back using the different diffeomorphism. And for example, so that's a property of the Floer homology is that theorem, there is a long exact sequence connecting Y, the Floer homology of Y, this Heegaard Floer homology of Y 0, and the Heegaard Floer homology of Y1. So it doesn't really tell you that knowing the Heegaard Floer homology of Y, you can tell the Heegaard Floer homology of any surgery, but I guess I should say here K. But at least it will give you some kind of relationship between different surgeries. And for example, if you know that this and this is not too complicated, you'll be able to say that this third one cannot be very complicated either. And luckily, in some cases, you can use this, and and answer in the negative problems like if I have two three manifolds, explicit three manifolds of Y1 and Y2, can I go from Y1 to Y2 by doing just one surgery? I mean, it's a fairly easy thing to prove that just starting from S3, if you do finitely many surgeries, you can get to any three manifold. But it's a meaningful question whether I can go by doing just one surgery. So let me mention some applications in these directions. So one. So one is the following theorem that says that if K in S3 is not the unknown, then thank you. Then when you take surgeries along K, then this is never RP3. Just a remark that S3 to the R0 is RP3. Okay. In fact, 3 2 over Q is also RP3. So this is a theorem of Kronheimer, Mrówka, Peter and me, that uses exact sequences like this and some additional things, but in fact the first proof uses a slightly different Floer homology, not the Heegaard Floer homology, but the monopole Floer homology. So the original proof is using monopole Floer homology, but as it turns out, you can also use alternatively the Heegaard Floer homology as well. And in fact, there is a more, so this is easy to state. But there is a more general result which was a conjecture of Gordon that says that again case in S3 that says that if doing some surgery, say P over Q surgery along a knot is the same, here by this I mean orientation preserving diffeomorphism, the same as doing P over Q surgery along the R knot for a given PQ pair, then K is the same as the R knot. Well, I would like to mention that this is really important, that you are doing the same slope, you are doing the same kind of surgeries. Otherwise, this wouldn't be true. Also, the orientation preserving is still important. You can take the trefoil and do +5 surgery on it, and you will get -5 surgery on the R knot, in which actually says that if you relax the orientation preserving condition, that's no longer true. Now, I guess the last thing I would like to talk about today is another direction that at first sight seems completely unrelated to these things, but at the end we can see that in fact it's related to it. So this is about unknotting numbers. So what is the unknotting number? Well, let's start with a knot. Let's start with an easy one. Our favorite example, the trefoil. And the question is, well, we know that this is not a trivial knot. Now, what we like to understand is how non-trivial it is. And you can measure it with lots of different ways. You can compute the genus of the knot, you can compute the four-ball genus. The unknotting number is a slightly different version, but one which is sort of easiest to visualize. So here we take the knot and would like to move it around. Well, we have no hope to get the unknot if we don't do something drastic. So suppose we are allowing crossing changes. So we allow, here is the knot, I move it around, and at some point it will sort of hit itself, and I allow it to make a change like that. It's easy to do it in a diagram. So for example, I could just take this crossing and change it, right? And then you can immediately see that this is the unknot, right? So the unknotting number is the minimal number of crossing changes. Needed to, unknot. If you haven't seen this before, another suggested exercise is to show that in fact you can always do it in finitely many steps. It's not come as a surprise, but still proving it needs a little bit of work, but so this is okay, so this is called this is denoted u of k, and so like u of k is always less than infinity. I guess one problem is to say something about the unknotting number. So let me try to illustrate this problem in one something. So in this case, right, the trefoil, well, we claim that the trefoil has unknotting number 1, and that's easy to see because it cannot have unknotting number 0 because that would mean it's a trivial knot, right? And we already were able to unknot it in one step, so the unknotting number has to be 1. And there are some classical invariants that bound the unknotting number. And some cases they work perfectly fine. In some other cases it's more complicated, so looking for a picture. A slightly more interesting example is an 8 crossing knot. Okay, let me look at this picture. Great, so this is a knot. In some knot tables I think it goes under the name 810. And if you look at this knot for some time, you can see that, for example, changing these 2 crossings will unknot it. So I guess it follows that the unknotting number of 810 is less than or equal to 2, right? So the question is, can it be 1? And it seems like such an easy problem. So we would like to clarify what we really need to check here. So of course, in finite time, I could just look at all the pairs of 2 crossings here, right? And check that if I change these 2, I don't get the unknot, right? And change these two. I'm sorry. I could look at and change this crossing and see that I don't get the or not. I can look at this, change it, and I see that I don't get the or not. And there are 8 crossings, I have to check 8 examples. But that's not enough. Because what is the unknotting number? It's that I have the knot in S3 and I'm free to move it any which way I want to. So basically, one way to say that is that I have to look at all the possible projections of the knot into R2, and in all the possible projections, which are infinitely many, I have to check all the possible crossings and see that none of them are not the knot, right? So I have to do infinitely many things. But on the other hand, if you like the picture that we have, we can fix the picture. But then, what is this unknotting operation do? It moves this picture around until we get a crossing and then change it. So another way to look at that is that the unknotting operation corresponds to an arc. I can take this part and maybe that part, and I connect it by an arc, and I move these two things together through that arc, and then I change the crossing, right? So in that language, changing this crossing corresponds to this really short arc connecting these 2 points, right? But I could just look at these 2 points, connect them by this straight arc, or I can go into the picture, out, into again, lots of times, and then come back, and then that will be also a crossing change. And I really have to look at all the possible such moves, and have to check that none of them will unknot it. So that's really the problem that we face. And luckily, so I guess the problem here, given a knot, so I guess this is an easier problem than just computing the unknotting number, slightly easier. Given a knot, K, can we tell whether the unknotting number of K is equal to 1 or not? So here we are looking at an easier problem. Is it possible to unknot R knot in one step? Okay. And most of the work so this seems like an easy problem, but it was studied by several people, and most of the work uses something that's called the Montesinos tree. So this is a lemma that says that if the unknotting number of K is 1, then have to explain these things. So then there is a number C, and so there is a knot C, and I'm sorry, with the property that the double branch cover of K, which I'm going to explain, is the same as doing n/2 surgery along C. So this is the double branch cover of S3 branched. Okay. So what that is that I first delete the unknot from S3. So S3 minus, delete K from S3. So the first homology of that is Z. So we have a map from pi 1 of S3 minus K into here and from here to Z mod 2. And looking at the composite gives us a map from the fundamental group to Z2, and that induces a double cover of the knot complement. And then you can glue back the knot. So that's that will be the branch double cover of K along S3. That's always another oriented 3 manifold. And the claim is that if U of K is 1, then in fact this double branch cover can be given as a surgery along some other knot C. Why is that? Here we can look into this operation of unknotting. I started maybe 5 minutes late, so can I use 2 more minutes? Okay. So here, this is K originally, and we are looking at the branch double cover. So inside the branch double cover, I could just take that part of the branch double cover of this ball, branch along these 2 arcs. Okay? So look at inside D of K, there is the branch cover of B3, branch along these 2 arcs. The boundary of that would be a branch double cover of the sphere, branch along 4 points. So the boundary of that is a torus. And it's easy to see that in fact, so the first thing that I claim, that this is a solid torus, S1 cross D2. This is a local computation that, if you don't believe me, that's another homework. So what are we doing here? When we change the crossing, right, we also change the double cover, right? So here, this is the knot K, but when we change our crossing, then we get another knot, which is supposed to be the unknot, right? So there is this local operation on the branch double cover that starts at D of K and ends at the branch double cover of U, which you can prove that's the same as S3. So there is this local operation, and well, what is that local operation? It's taking out the branch cover of this ball, the boundary of that is a torus, and then glue it back, glue back the same thing but sort of differently. So this is really a surgery, because you are cutting out S1 cross D2 and you're gluing back another S1 cross D2. All you have to understand is how different the first surgery from the other one. And in both cases there is a meridian, there is a circle that bounds inside S1 cross D2. You just have to look at the intersection number of these 2 things. If you do that, turns out that they intersect in 2 points, and that corresponds to these 2 right here. So that's really an elementary computation. But the outcome is that if am I really desperate, I really would like to prove that U of K is not 1, all I have to prove that when I take the branch double cover of K, that can never be realized as some surgery, N over 2 surgery along C. So what we need here is some kind of obstruction for a given knot. We can explicitly understand its branch double cover, but we need an obstruction to say that this is cannot be realized as a surgery like that. In special cases, this can be done. So there's some classical result of licorice. There is also a result when K is a two-bridge knot. In that case, this double branch cover is a length space, and then there is a famous result of Kohler, Gordon, Luckey, and Shalen that proves that in that case C has to be also a torus knot. So as it turns out, using that famous result and this Montesinos trick for special knots, those knots where the double branch cover is a length space, this is completely understood. And there is also some recent work of Gordon and Luckey. I guess Cameron will talk about that perhaps in his course, that is a great improvement of this result, and for special knots also gives you obstructions to realize this knot, this covered by n over 2 surgeries. But and you can also use the Heegaard Floer homology. After all, in that case, again for special knots, the Floer homology of that can be understood, and we already seen that understanding the Floer homology of surgeries is also a possibility, and so we have also some results in this direction. One of the results is that, for example, that U of A10 is equal to 2. So seems like a small result. I guess the point is that there are lots of knots, and some of them can be unknotted in one step. So that's good. We know that for those the unknotting number is 1. There are some classical obstructions, signature. You can also compute the first homology of the double branch cover. From this Montesinos trick you see that has to be cyclic. And that works also. So you can rule out lots of knots by classical results. You can also rule out some knots by this result. Some knots are two-bridge knots. And there is this one knot left among the 8 or less crossing knots for which they didn't know what the unknotting number was. And we tried our obstruction and it worked. So we tried for some other 9 crossing knots, and it worked too. So I guess putting these results together with this recent result of Gordon and Luckey, now all the knots that have crossing 10 or less are classified to have unknotting number 1, and the 11 crossing knots I don't think anybody have looked at. Okay, sorry, so I guess next time I'm going to talk about the construction, the Heegaard Floer homology, and go slowly.